There's a proof in math so complex and elaborate that it is considered one of the greatest works of logic in human history. The two mathematicians who wrote it, Bertrand Russell and A.N. Whitehead, won an Order of Merit in 1949 and the Nobel Prize in Literature in 1950. This proof brings into question the very fabric that holds the field of mathematics together. And here's what it proves. That's right, a proof of the very first math you learn in kindergarten won two mathematicians a Nobel Prize. Well, I'm kind of cheating. The proof isn't just this equation. The proof explains why this equation can even work at all, and in doing so, defines the very concept of addition itself. It looks a little more like this. Now this proof is long, and I mean really long, 300 pages long, and it's filled with a smattering of antiquated notation, but I sifted through it so you don't have to. This proof relies heavily on set theory, the study of collections of objects. For simplicity's sake, we'll be looking at set A, a tree, a bicycle, and a person, and set B, a tree, a person, and a stop sign. The most important operations you can do to these sets are union and intersection. A union is simply putting both sets together and making sure there are no repeating elements in this set. So A union B creates this new set, C. An intersection creates a new set that only contains elements that are in both sets. So A intersect B creates this new set, D. The last thing to know is that an empty set is a set with no elements. With these rules, we can establish the logic behind our proof. Set A and set B are separate and each have one distinct element if their union has two elements. Set A has element X and set B has element Y. The intersection of A and B is the empty set. This makes sense because the two elements are different, and intersection is only the common elements between sets. A equals X and B equals Y. Then A union B has two elements if A intersection B is the empty set. And now the proof seems rather obvious. If every number 1 represents a set of one element, each infinitely distinct from every other, and 2 represents a set of two elements, we've completed the logical bridge between set theory and addition notation. Two different sets, each with one element added together, make a set of two elements. So why does this matter? Logically, an object and another object grouped together result in two objects. But it's our ability to define these terms in math that separates us. The human species has created a language that not only explains the laws of the universe, but often explains phenomena before we can even observe them. This proof is our way of backtracking, of checking our old math with the advanced methods we have now. Our collective understanding of math requires proofs of the mundane to cement the axioms that are built off of simple addition. We need proofs like this because it reminds us that if we build a bridge without sturdy support, it's doomed to collapse. Thanks for watching.